Hello class and welcome to the Math 1030 video for handout for Unit 9C, which is exponential modeling. So let's take a look at exponential modeling ideas for applying to real life and to solidify what we've been learning already. Our first question here, we have a town situation. So we're going to model this town population with an exponential model. Given a town population with 10,000 people and a growth rate of 20% per year, how many people will live in the town after 1 year? So a couple of key things from our problem is population is 10,000 people, and the growth rate is 20% per year. Okay? This is an exponential situation because we're taking the increase is by the relative amount, the same relative amount, 20% every year. So it takes out how many people are there and increases that by 20%. So how many people will live in the town after 1 year? So the current population is 10,000. The growth rate is 20%. So with the growth rate, of 20%, the population is 20% more the next year, in 1 year. So the population will be 20% more after the first year. Okay, so how can we calculate that? Well, the first way goes like this. We'll take our 20%, which is 0.2 times 10,000. And then that's equal to 2,000. We can do that in our calculator or in our heads with 2,000. Which means that we'll add on 2,000 more people at to the 10,000 from the beginning of the year. So therefore, the population after the end of the year is 10,000 plus 2,000, which happens to be 12,000 people. Okay, so let's take a look at way 2. The second way might be a bit shorter. If we notice that 10,000 represents 100% of the population, and 2,000 represents 20%, then all we have to do is multiply the 10,000 by 120%. Okay. Let's show this by moving all of this over a little bit. So 20% or 1.2 will still give you 12,000 people. What about the population after 2 years? Well, there's actually we can take a look at this in 3 ways. The first way, we can take our population after 1 year, 12,000 people, and multiply by the 20%, 0.2 to find the 20% of 12,000, which we get 2,400. Then we add that on to 12,000. And when we do that, we get 14,400 people. Let's take a look at another way. Again, we're going to use the 1.2 idea right here. So if we take our 12,000, and multiply by 1.2, we'll get instantly the 14,400. Way number 3. Let's take a look at to calculate the population after 2 years. Let's include the population after 1 year in our calculation. So we have 10,000 times 1.2. Then multiply that by 1.2. We'll do that for the first year and the second year. So this is the population after 1 year. And then if I multiply it by 1.2 again, I'll get the population after 2 years. So that's this one. So note that I'm multiplying the population by 1.2 twice. Okay. So this part right here is actually, when I multiply it by, I make that squared, okay? Same thing as 10,000. Times 1.2 squared. Okay. When I do that, I get 10,000 times 1.44, which is equal to 14,400 people. Okay, so there's 3 ways of getting this. We usually favor way 3 because it's the fastest. Okay, so this is the 2, which means time equals 2 years. So we use the t as the exponent. So what would be the population after any number of years? T years. Take our initial value, 10,000, times by 1.2 to the t, just like we did at way 3. So that's our exponential function. So what is it exactly? Well, it's a function that grows or decays by the same relative amount. And just like we said, with the population growth, we have it growing by 20%. You take 20% of everything that's there and add that on. So we'll keep getting faster at growing faster at a faster rate. The formula itself is a general formula, so that means we can use it throughout this section in word problems with context to real life in exponential situations. The quantity that we want is equal to the quantity at time 0 multiplied by 1 plus r, the rate of growth by time, to the t. What do all these variables mean? Well, the first one is q. Q is the value of the quantity at time t. Q sub 0, or the Q naught they call it, is the initial value of the quantity at time equals 0. It's the initial value, or the quantity at time t equals 0. Then we have R. R is the fractional growth rate. Or it's the fractional decay if R is less than 0. And t, of course, is time. Could be measured in years, weeks, whatever the growth rate is measured in. So it's measured with the same units as R. So if R is a fractional growth rate of 20% per week, then T is in number of weeks. If R is the percent per year, then T is going to be time in years. Now let's move on to an example where we can use our growth rate formula in a real-life situation. This one is an exponential growth example. Ogden has a growth rate of about 0.7% per year. In 2016, the population was about 84,900. So what is the population of Ogden in 2020? So let's take a look at some of our values here that they give us. 0.7% per year. Okay, that sounds like it could be R, our rate. The population was 84,900. That sounds like an initial value, or the Q sub 0. Okay, so those are what we're starting with. Let's go up to here a little bit, see what we need. Q, the quantity that we want, is what we are solving for in this situation. Q naught times 1 plus R to the T. Okay, so I write down my formula, then I substitute in everything I know. So the Q is the quantity that I still want, and I don't know what that is, so I'll still leave it as a variable. My Q sub 0 is 84,900 people. Times 1 is still 1, plus R. The rate is 0.07%. So 0.7%, which is equal to 0.007. Okay, because the decimal used to be here and I moved it twice over this way. Okay, so I need to do one less here. 0.07007. So it started here and went this way. Okay, so that's what R is. So I'm going to substitute that in. To the T, now T is derived from my 2016 to 2020. So T is equal to 4. 2016, 2020. T is equal to 4 years. That's what we'll put over here. Okay. Now let's go ahead and calculate this. Let's put on some more labels actually first. The quantity that I want is Ogden population in 2020. Okay, so here is our initial value. Again, Q sub 0. Here's our growth rate. And here's the time. All right, moving on, we have Q is equal to 84,900 times 1.007 to the fourth power. Q is equal to 84,900 times 1.20283. That's the approximate and answer for Q. and which is equal to 87,302. Okay, so that's how many people will live in Ogden, or are living in Ogden in about 2020. Let's go on to an exponential decay example. Okay, West Virginia has a negative growth rate. It grows negatively about 0.5% per year, so it loses that many people per year. In 2015, the population was about 1.83 million. What was the population of West Virginia in 2020? What is the population? Okay, so we're going to have our formula, the quantity that we want, the initial value, the rate of growth, which is negative in this case, and time. So let's take a look at what values we have here. The growth rate, 0.5% per year, negative 0.5% per year. The population was about 1.3 million. That'll be our initial value. What is the population in 2020? And that would be derived from T. So let's take a look at what we need for our variables. Our rate, R, is equal to minus 0.5%, which is equal to minus 0.005. Okay? Because I moved my decimal 2 places to the left. So that's my R. The population at 1.83 million was the initial population. And then time is equal to 5 years, because I'm going from 2015 to 2020. So let's go ahead and put in our values. The Q sub 0 is 1.83 million people. So I multiply it by 1 plus 0.005. To the 5 years, because that's the difference between 2015 and 2020. Okay, great. So again, this is what we're looking for is Q, the West Virginia population in 2020. And then I'm going to see what equals, so I start with my initial value, which is 1.83 million. Q sub 0. This right here is the growth rate. R. In this case, it's negative. And this is time. Let's go ahead and solve this. So this Q is equal to, I'll add it to 1.83 million. Times times 1.005 to the 5th power. That's equal to 1.83 million times, well, it's approximately equal to because we have the 1.005 to the 5th is not exactly this number of, I made a mistake here. This should be subtraction, right? When you have a negative growth rate, you need to subtract it off. And when I do that, I'm not having 1.005 to the 5th. I'm doing 0.995 to the 5th. Which when I do that, I get 0.9752. Goes on forevermore, so it's about equal to that. And our next step is to go ahead and multiply those together. You get 1.7978 million people in West Virginia. Okay, so in this section, there are some logarithm calculations that you'll have to use to find the answers to some real-world problems. So let's go ahead and take a moment to practice solving for x using logarithms. Now, logarithm, again, is the inverse operation to exponents. Okay. So, logarithms. Okay, so if I raise something to a certain power, okay, all right, so if I raise a variable to a certain power, then the logarithm can take that out of the power in this way. 2 to the x is 50. Now I need to get x by itself, but x is being used as an exponent. So if I take my exponent and I find the logarithm of it, then I will be able to get x by itself in this fashion. I will take the log to the base 10 of both sides. Now, since there is no number written down by the log word, then we assume that it is log base 10. Okay? And so our calculator will say log base 10 or just log as well. One of the properties of logarithms is this: if you take a log of an exponent, then the exponent can be taken from the whatever you're taking the log of and put into the front of your logarithm, and you'll get something like this: x times the log of 2 to the of 2, because the x was put in front. Okay, so if you have an exponent as a logarithm, it can become a product, a scalar product, to the front. Okay. Our next step is to solve for x is divide by both sides by log 2. And so what we're going to do is we have these will cancel here, and I will have x on the left side of my equation. Log base 10 of 50 for log base 10 of 2. Okay, and log base 10 of 50 has a decimal approximation, which is 1 point. Well, actually, since it's approximately, gotta do the squiggles here. So it's 1.69897. Divide that by log 2, which is 0.30103. So that means that x is equal to 5.64. In this next example, we have 3 to the power of 4x equal to 100. And so what we're going to do is still use log to the base 10 to help us bring the x term out of the exponent, out of the power, and put it in front, and then solve it for x. So we're going to do log of both sides. So we can do log of 3 to the 4x is equal to log of 100. So these are log to the base 10s again, even though they don't write a power down there. And we can take this 4x and now move it to the front of the logarithm, and by that property of logs. So we have 4x times log of 3, log to the base 10 of 3, is still log to the base log of 100 there. Now we go ahead and divide both sides by log base 3. To isolate the x term, so those cancel, and now we have 4x is equal to log to the base 100, log to the base 10 of 100, divided by log to the base 10 of 3. And that's going to be equal to log to the base 10 of 100. You type that in a calculator and get 2. Log to the base 10 of 3 is 0.47712. So we can use those. Sorry about that. Use that on our calculator. Do 2 divided by 0.47712. So 4x is about equal to 4.1918. Okay. Then we divide both sides by 4. Those cancel. And we get x is equal to 1.048. Okay. So we can use logarithms to help us if there's an exponent in the power. So if there's an x, so there's a variable in the exponent position. Okay. Let's keep going. Number 2 more examples here. Log to the base 10 of x equals 6. Okay. And our clue here is base 10. They could have said just log x, but they wrote down base 10, which means I'm going to do the opposite as what I did before. So before, when I wanted to get the variable out of the exponent position, I did log both sides. But now I have the variable tied into the logarithm, and so I need to do that side of the equation to the power of a base that's the same. So we're going to take 10 and put it to the log base 10 of x equals 10 to the 6th. Okay, so if I raise both of the sides of the equation to a power of 10, and therefore we'll maintain equality. Now, since exponents and logarithms have inverse operations, this will cancel right here. 10 to the log 10 is just 1, and therefore it becomes 1 times x. And we have x just by itself, and so that's why we raised it to the 10th power, to the power of 10. So 10 to that power, I mean. So x is going to equal 10 to the 6th, which we can calculate with our calculators or with a knowledge that 10 to the 6th is 1,000,000. Okay. Let's take a look at this next one, log to the base 10 of 5 plus x equals 2. Okay, so I'm going to note my logarithm again. It's base 10. So use that to to say, okay, I'm going to do 10 to the log base 10 of 5 plus x equals 10 squared, okay? Raising both sides to the 10th. Now when I do log 10 to the log of 10, I just take that, whatever is in the parentheses there, 5 plus x, and put that down out of the exponent position, and the 10 to the log 10 will simplify to disappear because they're inverses of each other. And that's going to equal 10 squared. So copying that through. 10 squared is 100. So let's go ahead and write 100 down here. And then 5 plus x equals 100. I just have to subtract 5 from both sides. And when I do that, we get x is equal to 95. Okay. Next, we're going to graph our exponential functions. Let's take a look at an example situation. Your starting salary at a new job is $2,000 per month in dollars. At the end of each year, your monthly salary increases 5%. Create an exponential function equation to model the situation using the formula from number 3. Okay, so the formula from number 3, as we recall, is Q, quantity, equals Q sub 0, the initial value, times 1 plus R, the growth rate, to the t power. Okay, so we're going to create an exponential function with this situation. Let's take a look at what information they give us. The salary is starting at $2,000 per month. At the end of each year, the salary increases 5%. Okay. So I need to do a function, okay, which is key. That means I'm not going to put in numbers for every variable, okay, because the function will have some constants and then the rest will vary. So Q will vary because that's the quantity, depends on stuff like the time. How long you've been in the job, okay, will determine how much your salary is. Now Q sub 0, or the initial value, Q naught, is $2,000 per month. And multiply that by 1 plus R, which is 0.05, to the t. Now t can be anything. We want our function to model the salary at any time, whether it be now, or 1 year from now, or 10 years from now. Or months, since the rate is 5%. Oh, the monthly salary increases 5% at the end of each year. So yeah, time will be in years. So what we have here is that t is what rules the whole equation, okay? And that's what we will say is our independent variable. Okay. And Q is what we are looking for, and that does depend on t. So we call that the dependent variable. So what we need to do now is we need to create a table. Okay. In order to graph something, we're going to create the table so we can have a table of values. We need to create a table showing the value of the quantity Q for the first 5 units of time. Okay, 5 units of time, which would be 5 years in our case. Okay. All right, so let's create our table. Our independent variable goes first, because that's what we'll just put in the values. And our dependent variable will calculate. When you create a table, you can put in any number of values, but it says in any value. that you want for t, but it says that we need to do the first 5 units of time or the first 5 years. He said t, 0, we know that one's easy. 1, 2, 3, 4, 5. Okay. So Q we've done to help calculate all this stuff. Q is equal to $2,000. So this is Q at time 0. $2,000. Well, Q is $2,000 at time 0. Okay, so let's go ahead and write that in. Okay. Now, Q at time 1. Let's do that next. At the first year, we have Q as the t is going to be 1. And so we want to show what Q is. So we take our $2,000, multiply by 1.05. We get $2,100. So this is going to be $2,100. Q is going to be equal to, at time 2 years. We can still use our initial value, 1 plus 0.05 to the 2. That's equal to 2,000 times 1.1025. And that's equal to 2205. Move this down just a tad, move it up just a tad. So make room for one more calculation. So for the third year, we take 2,000, we multiply by 1.05 to the third, and shorten this up a bit. And when I do that, I get $2,315.25. Okay. So we can put in our table here, the year 2 was 2205, year 3 is 2315.25. Year 4, we'll put here. So Q is equal to $2,000 times 1.05 to the 4th power. Okay, so that's equal to 2,431 and 1 cent. Okay, so put that in our table. Okay, move our table over just a tad. And then at year 5 here, our last one, the quantity is going to equal $2,000 times 1.05 to the 5th power. Oops. Okay. Which we do, that we get 2,200, oops, sorry, $2,552.56. Okay. All right, so moving forward, we need to make a graph of this situation. When we start our graph, we draw in the axes. Okay, that's 0 and that's 0. On this bottom axis is time in years. Okay, and we have 5 years, so 0, 1, 2, 3, 4, 5. Okay, so that's all ready. And then on our vertical axis, we need to think about the numbers here. Okay, there's what the lowest number and the highest number is. It begins at 2,000, but it goes up to about 2,500, just over that. So we can go ahead and make our lowest number 2,000. So we'll put in a break there. And that's going to be 2,000. And then we get all the way up to 2,500. It's a little bit above that. Okay, so 2,100, 2,200, 2,300, 2,400, 2,500. Okay, let's think about what we can title this axis. This is the monthly salary. That is happening, and that will be in dollars. Okay, so let's bring that down a little bit. Okay, the monthly salary in dollars. Now we're going to go ahead and plot the points that are in our table. So since at time 0, we have 2,000. Put a big dot here. And our next value at year 1 is 2,100. So we can go exactly up here. Year 2 is 2,205, so we can go exactly just a little bit above 2,200. And 2,315 for year 3. Year 4 is 2,431. And then 2,551. So right there. Now this looks a little bit linear, but it'll curve up more even. Okay. There's a little bit of a curve to it. Okay, so there's our exponential function graph. The next example, we talk about exponential decay and a graph of that. A certain drug breaks down in the human body at the rate of 15% per hour. The initial amount of the drug in the bloodstream is 8 milligrams. Okay, so this is a very typical decay example, which is great because you want to track, a lot of times you want to track out how much medication will be in your bloodstream, so you can know when to take more or to think of it medical purposes. Let's say you're in a medical job. This is analogous to a situation in the book chapter, which talks about the decay of alcohol percent in the bloodstream, so that decays after time. So let's take a look at this example. Create an exponential function equation to model the situation using the formula from number 3. Okay, so our formula again is Q, the quantity that we have, is equal to Q sub 0 times 1 plus r to the t. So q is equal to, in this case, q is equal to the initial amount, which is 8 milligrams. Okay, so the initial amount is 8 milligrams. The growth rate is 15% per hour. Okay, so that's our time is in hours. We do a minus here because it's going to be a decay, so 0.15 to the t. So is it going to be an equation again? We don't know what that is. It could be for any amount of time. Okay, then that will equal, so q will then equal 8 times 0.85 to the t. So there is our equation. Function. There. We want to create a table of values showing q for the first 5 units of time. So this is going to be in hours, because notice that the rate is hours. All right, so our time, 0, 1, 2, 3, 4, 5. We'll keep track of our quantity in the bloodstream in milligrams. We know that at time 0 is 8 milligrams. Now what we're going to do is we're going to calculate the next quantity. So at time 1, okay, so q is equal to 8 times 0.85 to the first power, because after 1 hour, this is how much is going to be in the bloodstream. That's 8 times 0.85. Which is equal to 6.8 milligrams. Okay, so we can put 6.8 in our table. At year 2, q is equal to 8 times 0.85 squared, which is equal to 8 times 0.7225, which is equal to 5.78 milligrams. Okay, notice that is decreasing here. Now that we have finished all of our data points, our table is now complete. We've calculated the quantity of the lidocaine in the bloodstream over the next 5 hours, the first 5 hours. We're going to make a graph of the exponential function here. So for our graph, we'll need our coordinate axes. We'll need our time in hours. Okay, so we need to make that here a bit taller. There's room for our label here. Okay, so that's our time in hours. On the Vertical axis, we have the amount of drug in milligrams. Our highest value is 8, so it starts at 8 milligrams and goes down to 0. So that's the amount of drug. In milligrams. Okay. So we'll pull that down a little bit. Okay, so we got to draw some intermediary points here. So let's do 4 milligrams, 1, and I'm going to do 2, and 1, and 2, and 3, 4, 5, and 6. Okay, so we have 8 milligrams at 0 times 0 first. Then we are going to go to our 1, which is at 6.8 milligrams. So we'll go down to 1, which is 6.8. So here's 6. So we're just going to be almost to 7. 5.78. So it's almost to 6 for our 2. 4.913, which is about 5 for our 3. Oops. It's right here. And 4.17, which is just over 4 for our 4. And for our 5, we have 3.5. Right about there. Okay. So you can see that the line goes down at that rate. Okay. So now we have a graph of our exponential function, exponential decay on this one. Number 8 is our last concept here. We are going to take a look at some alternate forms of the exponential function using doubling time and half-life. Okay. So if q is equal to q naught, the equation for doubling time, or the exponential equation for doubling time, is similar to what we've already seen, 2 to the t divided by t double. Okay. And this is the key here to find t double. Okay, that's will help us get the right exponential rate. The exponential function with half-life is similar. So the quantity you want at a certain time is quantity times 0 times 1/2 to the t over t half. The time it takes to have half of your amount. Okay, that's also key. You find a piece of, let's go ahead and apply this to real life. You find a piece of cloth that was painted with organic dyes. By analyzing the dye in the cloth, you find that there's only 63% of the carbon-14 originally in the dye is remaining. So remember that carbon-14 is present in all living organisms, but doesn't start to decay until the organism's died. So once the dye is painted in the cloth and dyed in there, then it's left alone and the carbon-14 will decay. The half-life of carbon, again, is about 5,700 years. So when was the cloth painted? Okay, so the quantity left is given to us. Let's see what we got here. So 63% of the carbon-14 remains. This is going to be our quantity. Okay, that's our Q. The half-life of carbon is about 5,700 years. Okay, half-life is 5,700 years. That's our T half. When was the cloth painted? Okay, so those are all the only parts that we have. But let's take a look at what we need. We need to know when the cloth was painted, so we need T. So let's go ahead and write that down. So our formula in general is Q equals Q naught, Q sub 0, times 1/2, since it's half-life, to the T over T half. And that's going to equal, well, we don't know what Q naught is. Well, Q naught is how much of the quantity is at the start. So how much of the carbon-14 is in there at the start? Well, that's only 1. Okay, the whole thing is in there. Okay, and this could be done as a fraction. T we do not know. T half is 5,700 years. Okay, and the quantity that we have at present, Q, we said was 0.63. So here's our formula, and we just need to solve for T. What we have is that T is kind of caught up into this exponent spot. And the opposite of exponents is logarithms. The inverse of exponents are logarithms. So we have to do logarithm. Let's do log to base 10 because it's the easiest. So I'm going to take the log of both sides. Okay, and this is what we get there. With this part, we can take our logarithm exponent as we simplify for solve for T. We get that, take that and put it into the front of the logarithm. Okay, and when we do that, we have the log of 0.63 is equal to T over 5,700 times the log of 1/2, because 1 times 1/2 is 1/2. Okay. So continuing on over here, this next column, the log of 0.63, we got to get, the log of 0.63, let's find out what that is. Okay, so that's going to be minus 2 minus 0.2. And then we have, it's 2.00 minus 2.20066. Okay, so it's really close to minus 0.2. And that's going to equal T over 5,700 times the log of 2, which is 0.30103. Okay. Now let's divide both sides by 0.30103, which is going to be give me the T over 5,700. So we're getting step by step closer to isolating T. Now when I divide that on those two, okay, so I take that log of 0.63 divided by the log of 1/2, and then we get T over 5,700 make that bigger here. Is equal to 0.6666. Okay, and then when we multiply by 5,700, T is going to equal 3799.48. Or approximately equal to 3,800 years. Okay. All right, and that's our video for this section. Please let me know if you have any questions.